Hello everybody. Let's talk about index notation or tensor notation in the context of classical mechanics. We will discuss in this video about summation, Kronecker Delta, and Levi-Civita tensor. We will not discuss about Einstein notation or Einstein convention, which could be in a separate video. So I'm Professor Ricardo Gomes from the Physics Institute of the Federal University of Goiás, and let's start with summation. Consider these terms. We have n terms, a1 plus a2 plus a3 plus up to an, and the result of it is s. So we can write this very long expression here in a more compact form using the summation symbol. So you can see here that this result here, S, is equal to the sum of ai with I from 1 to n. So I is going to be 1, 2, 3, up to n. And we will have a1 plus a2 the same way that we have here. There is nothing special on this index I, which could be changed to any other letter, for instance J, K. We used to call these dummy index. The sum does not depend on the index I. So we can write as using a summation with the index J of the terms AJ, or the same using the index K, and so on. Now let's talk about product, just for completeness. Consider a sequence of a1 multiplying a2 multiplying a3 and so on up to an, and this is equal to t. We can write this expression in a more compact form using this product symbol, the capital Pi letter, of the terms ai with I from 1 to n. So this is going to be exactly the same thing of this, a1 multiplying a2 and so on. I is a dummy index in the same way we described for the summation. And then t is also equal to the product of aj with j from 1 to n, and the same thing for k, and so on. Double summation. So consider this double summation. Double in the sense that we have two indices, I and j, both from 1 to n. And we are summing these terms bij, two indices. And this is equal to sigma. So this double summation is the same as we consider two single summations, one in j and the other one in I. So, being more explicit, d sigma is, for instance, let's fix the I being equal to 1, and j will go from 1 to n. So we will have b1 1 plus b1 2 up to b1 n. So the first index of this b term is 1, the same as here and here, and the second index is going from 1, 2 up to n. So you have all these terms here. For I equal 2, you will have also the j from 1, 2 up to n, and so on, The same thing for I equal to n, and then j will be 1, 2, up to n. It is very obvious that this summation of bij is the same of the summation of bji, because if we have b12 and then b21, here we will have the same two terms, b21 and then b12, b1n and then bn1. Doesn't matter the order of the sequence of additions. So we can exchange the position here of the indices in the bij or bji. Also, we can keep here bij and change the order of the indices in the summation symbol instead of ij, ji. And the other possibility is change the order here and change the order here. So all this is exactly the same. And it is also obvious that we can change the letters I and j to k and l, or m and n, and so on. So higher order sums are generalizations of the double sum. So you have here the single sum with one index, double sum, and you will have generalizations of it the same way as we did for the double sum. We can use these in the context of system of equations. So consider this equation, the equation number 1, so this is y1 being equal to a function of the x variables. So you have x1, x2, xn, and you will have an addition of this kind of term, a coefficient times the x. The first index of the coefficient being equal to 1 in all of them, because it is related to the first equation, to this one of the first equation. The second index, it is related to the x variable. So 1 and 1, 2, 2, and n. The second equation then, the coefficient, the first index of the coefficient is 2, and the second coefficient is related to the variable x. So you have another function of the x terms, and so on up to the m equation. So this is going to be am1, am2, amn. You have m equations of y as a function of x and n variables x. This is very hard to write, so we can write it in a much more compact form. So each of these equations here can be written as yi being equal to the summation of the coefficient aij multiplying xj, and the j from 1 to n. So since this is the I equation, the first index of the coefficient is I as the variable y here. Of course, if we want all the system of equations, then the I must go from 1 up to m, where in this case this index is called free index. It is not indicating a summation, it is only indicating the equation that we are considering. In that sense, we can change it, for instance, to k. Instead of I, we can use k. You see here, iaj, ik. And since this summation, it is considering the j index, we can change it to the m index as well, and the coefficient is going to be akm xm. Of course, now the k going from 1 up to m. Okay, now we are ready to discuss the Kronecker delta, delta ij. Delta ij is equal to 1 if I and j are equal, or it is equal to 0 if I and j are different. The main property of the Kronecker delta is this: the summation of delta KL AL, of the summation of this product of L coming from 1 up to n is equal to AK. So take a look at this. We can have L equal to 1, 2, 3, and if L is equal to K, then we will have delta K, K, AK, and in that situation, delta K, K is going to be 1. In any other situation, in any other terms of this summation, this delta is going to be 0. So when delta KK is equal to 1, when this guy is equal to 1, then the result of this summation is going to be AK. Of course, the K index going from 1 up to n, the same space interval that the index L is going. We discussed in words this idea, so let me demonstrate it. This term, the summation of delta KL AL, is equal to delta K1 A1 plus delta K2 A2 plus delta KK AK. The term before this one is going to be delta K K minus 1 AK minus 1. The term after this one is going to be delta K K plus 1 AK plus 1, and so on up to delta K N AN. Of course, this term is going to be 0 because K is different of K minus 1, K is different of 1, and so on. And the only one term that is not going to vanish is delta KK, which is going to be equal to 1, and the result of this is AK. Delta KK, AK is equal to AK. Okay, so another example of the use of the Kronecker delta, instead of having this term AL, now we have, for instance, TJK, and the delta is delta of IJ. So one of the indices is equal in the delta and in this term T. So since J is going from 1 to N, we will have the result, the TIK. Okay, now we are ready to discuss the Levi-Civita tensor, Epsilon IJK. This is also called Epsilon tensor or antisymmetric tensor, permutation symbol, alternating symbol. And the idea here is the epsilon is equal to +1 if the indices IJK is an even permutation of 1, 2, 3. And it is equal to -1 if IJK is an odd permutation of 1, 2, 3. In any other case, which results that if any two of the three indices IJK are equal, it is equal to 0. Let's discuss this better. So consider this sequence 1, 2, 3. If you do an interchange between 1 and 2, the position of them, This is an odd permutation, one permutation. So now we will have 2, 1, 3. So if you have a tensor with this sequence, it is going to be -1 because it is an odd permutation of 1, 2, 3. If you do one more permutation, for instance, interchanging 1 and 3, you will have 2, 3, 1. Then this is an even permutation. And this is equal to 1, 2, 3. The epsilon is invariant under cyclic permutation. So 1, 2, 3, the next one is going to be 1, and then 2, 3. So you have here 2, 3, 1, the next one is going to be 2. This is a cyclic permutation of each other. So it is equal. This being an even permutation of 1, 2, 3. So an epsilon with this sequence, or this, is going to be +1. In other words, if you have epsilon of 1, 2, 3, or 2, 3, 1, a cyclic permutation of this, and it is invariant under cyclic permutation, that's why this guy is called anticyclic permutation, or epsilon of 3, 1, 2, all of these are equal to +1. If you have an odd permutation of two indices, for instance, interchanging these guys here, or if you do an anticyclic permutation of these, you will have epsilon 1, 3, 2, or 2, 1, 3, or 3, 2, 1, and all of these are equal to -1. In any other case, the epsilon is 0. For instance, 1, 1, 1, 1, 1, 2, 1, 2, 1, etc. Okay, so now, being understood the idea of the epsilon, which is defined this way, consider two vectors. Vector A, the first, second, and third component being A1, A2, and A3, could be AX, AY, AZ, and another one, B, being its components B1, B2, and B3. The vector product, or the cross product, of A and B is equal to C. Okay, so this can be expressed, one of the components of C can be expressed as Ci, for instance, this could be 1, C1, is going to be a summation of these terms, with both J and K from 1 to 3. So a double sum. We are going to have 9 terms of this. And all of them will have AJ and BK. No I index in the A or B. This is what we expect for a cross product. So if this is going to be C1, the result is going to be A2, there will be a term with A2B3 and another one with A3B2. So let's see if this is what we are going to have. Of course, the I is going to be 1, 2, and 3 because we need all the 3 components of the C vector. Okay, for instance, let's consider the example that I was starting to describe, I equal to 1. So C1 is going to be, we know that we are going to have 9 terms. So the first 3 terms will be epsilon I, so epsilon 1 in all cases, and J is going to be 1, 1, 1, and the K is going to be 1, 2, and 3. So it's going to be J equal to 1 and K 1, 2, and 3. This is the idea. So the next 3 terms, we will have the I will always be 1 in this case. The J now is going to be 2, So A2, A2, A2. And the K is going to be 1 and 2 and 3. And we will have B1, B2, and B3. And the last three terms, epsilon 1, 3, 1, epsilon 1, 3, 2, and 1, 3, 3. So, following this definition here, this term is going to be 0 because two indices, actually here we have three indices being equal, so this epsilon is 0. Here two indices equal, then it is 0. The same for the next one. The same here, 1, 2, 1. 1, 2, 2, so this is 0. This is not going to be 0, but this is 0, 1, 3, 1. This is not, and this is 0, 1, 3, 3. So we have this term and this term. This epsilon is in this situation here. It's an even permutation of 1, 2, 3. So it is equal to plus 1. And this epsilon here is going to be minus 1 because it is an odd permutation of 1, 2, 3. So the result of C1 is going to be, I included the plus sign here just to emphasize that this is going to be the epsilon equal to plus 1 multiplying A2, B3. And this one is going to be minus 1, so minus A3, B2. Great. So now we're ready to discuss this useful identity. The summation of this product of epsilon tensors is equal to this product of delta, Kronecker deltas, minus this other product here. So to understand this better, or a little bit more easy, let me express that this epsilon here, as we already discussed, it is invariant under cyclic permutation. So it is the same of epsilon of LMK. Now, this epsilon and this epsilon being multiplied, the third index of them is the same, K. Okay, so let's try to understand this identity. Consider this term, the product. This term differs from zero only in two situations. The first one, if I is equal to L, if I, the first index, is equal to the first index here, and at the same time, J being equal to M. In that situation, both tensors will have the same sign. So if this is plus 1, this is plus 1 as well, and the product is going to be plus 1. The other situation where this term differs from 0 is when I is equal to M, the first index is equal to the second index of this tensor, and J is equal to L, J equal to L. So in that situation, this epsilon and this epsilon, they will have the product of them is going to be minus 1, because if one is plus 1, the other one is going to be minus 1. So the product is going to be minus 1. In the first situation, I is equal to L and J is equal to M. In this side of the equation here, we will have delta IL being equal to 1 because of this, and delta JM is equal to 1 as well. And this side is going to be 0 because I is equal to L only. If I is equal to L and it is equal to J as well, or equal to M, then the epsilons would be 0. This is not these are not the two situations that we are describing. And in the other situation, if I is equal to m, these guys here are going to be 0, and this is going to be 1, and j being equal to L, this delta is going to be 1 as well, and the product 1 times 1 is going to be plus 1, but with this minus, we'll have minus 1, the same way the product of those two epsilons that we described. So, as a result, this term, the summation of these terms, can be expressed as a combination of products of Kronecker deltas, the way that we would like to demonstrate this identity. Okay, to conclude, let's discuss some algebra with summation. The first situation, substitution. So consider this equation, AI, as a function of these b terms, and we have this coefficient here and the k from 1 to n. So we will have a coefficient times b1 and another one for b2 and so on up to n. So this is our first equation. And we know b as a function of c, and we want to substitute into equation 1 the b terms. To do that, so in other words, we want to write a as a function of the terms c. To do that, we need first to change the free index in 2 from I to k, because here it is bk, so I need to do that first. And we also need, because this is going to be k, we also need to change the dummy index k to any other letter not used yet, for instance L. So instead of these, we are going to write bk being equal to the summation of vkl cl. Okay, now we are ready to substitute these terms into the equation 1. Resulting in AI being, this is the sign for this is the symbol for a double summation. So we have the summation for k and the summation for L. Then the uik, vkl, cl. Okay, we're done. That's it. Another algebra. We will multiply sums. So consider this sum, which is equal to the letter p, the summation of ak, k going from 1 to n, and q being the summation of bk, k from 1 to n. You know, this k is a dummy index. The summation does not depend on the letter k, on the index k. So if we want to do the product of p multiplying q, we need to take care in using these summations with the same index. So we can change this k letter here to, for instance, L. So it's going to be the summation of L from 1 to n of the terms BL. And now we can do the product. So P multiplying Q is going to be the double summation of AKBL. In this situation, we guarantee that we will have the crossed products. For instance, A1, B2, A1, B3, and so on. B2, A2, B1. Because if you do multiply these by these directly, it would be these, which is different of the correct product. And this wrong result here, it is actually equal to this result, not the one that we would like, not equal to the correct one. You don't see the cross terms that I was talking about. Because if you do only this summation here, the result is going to be A1, B1, plus A2, B2, plus up to AN, BN. And we still have this summation of something that does not depend on key, or on the K letter. So it is going to be this term here being in a summation of another K index. So we will have n times this guy here, which is wrong. And factorization. So consider this equation, the summation of Tij and j, j from 1 to n, and one of the n terms here, the ni. And we want to factorize nj. So we will use the Kronecker Delta, and we will write that ni is equal to the summation of this product here, delta ij and j. So j will go from 1 to n. When j is equal to I, then this guy is going to be 1 and this is going to be ni. So if we insert this guy here into here, we will have this term, this is exactly the same, minus lambda times ni, which is this, summation of delta ij and j, equal to 0. Okay, let's take a look into this equation again. The constant lambda multiplying a sum is the same of a sum of each term multiplied by this constant. So I can write it, the lambda here. Both sums are in the same j from 1 to n, so we can write it as only one summation of this term, and the nj can be, we can write it here, and the term is going to be Tij minus lambda time multiplying delta ij, all these multiplying nj. So we just did our purpose, we factorized the nj term. Okay, the summary of our lecture, we discussed about summation, product, double, and generalizations of the summation symbol. We used that in the system of equations. We discussed the Kronecker Delta and the Levi-Civita tensor, and we did some algebra using summation. Useful reference for this is the Analytical Mechanics by Nivaldo Lemos. And I expect that this video can be useful for you, and to watch other videos like this, please subscribe. Thank you very much.